Okay, let's take a look at today's lesson. What we're going to be looking at really should be mostly review for you. I guess the difference is you probably would have done this over 4 or 5 days. We're going to do this over 1 day. So it's just a big review day. We're going to look at graphing polynomials and finding the zeros of polynomials. And the first thing I want to look at is graphing. I actually do not have an example on here of graphing. So you do have examples on your daily work of graphing. I'm going to take you through the steps of what you would do, but I am not going to do an example of it. Just want to make that clear. But this is what you would do. It may be different than what you did last year, so please be sure you're taking note of this. The first thing I would want you to do to graph a polynomial is we're going to determine the end behavior. The end behavior you probably worked with last year. This is a graph, a little chart of end behavior, and I'm going to talk about end behavior in just a moment. So step 1 to graphing a polynomial function, you figure out what the end behavior is. Step 2, you find the zeros. We're going to find the zeros. Since we're graphing, it's only important that you find the real zeros. I mean, if you want to find the imaginary zeros, that's fine. I'm not going to require you to if our purpose is graphing. We're not going to graph imaginary zeros. So we're going to look for the real zeros. Then this may be different. I don't know that they would have had you do this last year. Step 3, what we're going to do is make a t-chart that includes the test points between the zeros. So let me explain what that means. So let's say, I'm just going to adjust this so we can get an idea. So let's say we have it looks like that. Say that's our polynomial. And I have a 0 at, -2 and -4. Then on my t-chart, if my 0 is at -2, -4, I would need to find the value at -3. I would need to find the y value there. And what am I doing? I'm estimating a relative minimum. And it's an estimate. So we want to get to the middle. We want to be the middle of the zero. So let's say here that's like a -2, 1, 2, 3, 4, like 4. So what's exactly in the middle between -2 and 4 would be 2, right? -2 and 4 would be 1. -2 and 4. Yes. So then we would put that on our t-chart and we would find that value. Okay, so that's what that's an estimate of our relative maxes and mins. That's what that is. Okay, that's what's important. Now, it's not going to necessarily be the exact relative max and min, so we remember what those are, right? You've done those on a calculator before. You found the relative max and min on a calculator. They're like where it's the tallest or the lowest. That's a big deal in calculus, and there are calculus techniques to find the actual relative max and min. We're not going to go there. We're just going to estimate. What would the max or min be? That's the purpose of step 3, is to make a t-chart including the test points between the zeros. Okay? And then the last step would be to determine the multiplicity of the zero and match the shape. Okay, let's recall what that means. So if I have, let's say this is my polynomial, I have it factored. And this means I have a root at 1, and then I have 2 roots at -2, and I have 3 roots at 3, right? So if I have a multiplicity of 1, I have 1 root, then that's it's like a line. It's kind of cuts through. At 1, it would just kind of go through 1, cut through 1. If I have a multiplicity of 2 at like -2, that means it's a bounce. And so that takes us over to this chart right here. If the multiplicity is even, okay, bigger than 1, if it's even, it's like 2, 4, 6, 8, it's going to be like a parabola. It's going to bounce off of the x-axis. If the multiplicity is odd, okay, bigger than 1, like 3, 5, 7, then it's going to do like this little squiggly thing. It's going to look kind of like a cubic. It's going to kind of do this little squiggle through the x-axis. And so that's what I mean by determine the multiplicity of each zero and match the shape. So that's what we would be looking at. And you have a couple of examples of this on your daily work so you can practice it. And when you get to the daily work, they're like the first 2, you're going to follow this chart. You're going to follow these steps. This is what you're going to do to graph a polynomial for me, okay? So that's graphing. Let's talk about end behavior. Again, it's probably just a review from last year, but let's go ahead and cover that. Make sure we're clear. So if the degree of the polynomial is odd, In other words, like 3 or 5 or 7, the degree is the highest power, the number of that, that number, the highest power. So if it's like x cubed or x to the 5th, if it's odd and the leading coefficient is positive, the end behavior is going to start down and end up. If the leading coefficient is negative and the degree is odd, it's going to start up and end down. So that's something you just have to memorize. This notation, this formal notation, is pretty important. You probably looked at it last year. As x goes to negative infinity, as x is going smaller and smaller, f of x or y is getting smaller and smaller. So for example, a quiz or a test question, I might give you a polynomial and I might ask you to fill in the blanks here. What's happening? That's something that I would want you to know. I want you to understand what that notation means. As x gets larger and larger, as x is traveling this way, f of x, which is y, is also getting larger and larger. Okay, so that notation is important. Now, if the degree is even, 2, 4, 6, 8, like x squared, x to the 4th, then if the leading coefficient is positive, both ends go up. The end behavior is the same, both ends go up. And if the leading coefficient is negative, both ends go down. That's kind of a review for us. We okay with that? All right, let's take a look at the second. So that's graphing polynomials. That's all about graphing polynomials. Now let's look at zeros of polynomials. We have a few things to look at. One is rational roots theorem, P over Q. If you don't remember P over Q, then maybe it hasn't traumatized you as much as some of us. I am not that lucky with P over Q. It takes me several times to get it, but we're going to have an example of it. Let's talk about what rational roots theorem means. Well, first of all, it only works with rational roots. So now we've got to go into number theory. What is a rational number? So we have imaginary numbers, and they're in the form of a plus bi. That's an imaginary number. That's actually the big category, is imaginary, because all real numbers have a b value of 0. Okay, so we have imaginary numbers, we have real numbers. And underneath real numbers, we have rational and we have irrational. So let's talk about those differences. Rational numbers are numbers that can be written as fractions, like 1/2 or 5. They're an integer or they're a fraction. Irrational numbers would be like square root of 2 or pi. Those are irrational numbers. This theorem only finds rational roots. If you have imaginary roots or if you have irrational roots, it doesn't see them. It cannot find them. It can only find rational roots. Okay, so it is limited, and actually it's our last resort, right? We only use a rational root theorem P over Q when we've run out of options. Then we do all that synthetic division stuff, which you may or may not remember, but we'd have an example. So, what is this? What the theorem tells us, it tells us actually, it tells us that if the polynomial has a rational root, that it has to be in this set of numbers created by this fraction. This is P, this is Q. P are factors of the constant term, and Q is factors of the leading coefficient. And I have an example to remind you how to do that. Okay, so that's rational root theorem. Then we have another, this is actually called Descartes' rule of signs. This helps us determine how many real. Now that includes both kinds, rational and irrational. It's going to just tell us how many real roots that we have. So normally it's not a problem. Real zeros, the number of variations in sign in the polynomial, and that means the sign of the term, and I'll give you an example of that. So the number of positive real zeros is equal to the number of variations in sign. Okay, or, this is where students get confused, or is less than that by an even whole number. What in the world is that about? Or is less than that by an even whole number? Well, we just talked about that this theorem does not take into account any imaginaries. And our little imaginary friends, right, they come in pairs. They're lonely. They don't want to be by themselves. They're imaginary already, right? So they're always in pairs. So if you have a root I, then you're going to have its conjugate, negative I, is also going to be a root. So we have to take into account that. So let's say we have 5 variations in sign. That means we have 5 positive real zeros, or we have 3, or we have 1. Why? Well, I could have, let's look at this possible. I could have 5 real zeros. That's possible. I could. Or I could have 3 real zeros and 2 imaginaries. Or I could have 1 real zero and 4 imaginaries. Do you see why we have to go down by a factor of 2? Because we don't know if we have imaginaries or not. This is taking into account what if we have imaginaries. That's why. That's why we have this or is less than by an even whole number, which usually just totally confuses students. But that's why. Alright, and then if we want to find the number of negative real zeros, the first thing we'd have to do is find p of negative x, and then do the same procedure. It's going to be the number of variations in sign, or less than that by an even whole number. And I'll take you through an example of that that will make sense, hopefully. Fundamental theorem of algebra, it's fundamental, right? It's a pretty big deal. It tells us 3 things. It tells us that every polynomial of n degree has exactly n zeros. For example, if I have a polynomial x to the 5th, this polynomial is going to have exactly 5 zeros. Exactly 5. Now, I don't know which ones. They could be real, they could be imaginary, they could be rational or irrational, but it's going to have 5. That's what the fundamental theorem of algebra tells us. Also, it tells us that if a complex number is a 0, then its conjugate is also a 0. That's why I was talking. The imaginaries come in pairs. They never go by themselves, right? So if I have one imaginary 0 of, I don't know, 1 minus I, then I have 1 plus I is also imaginary 0. They're in pairs. And then the last thing is every polynomial can be factored into a product of linear and irreducible quadratic factors. Those vocabulary words are a big deal. We use them in calculus. A linear factor. A linear factor is like x plus 2 to the first power. That's a linear factor. Right, that's a linear factor. Irreducible quadratic, an example of an irreducible quadratic would be x squared plus 4. It's a quadratic factor. It's irreducible because if I were to try to factor this, I would need the zeros of it, and the zeros of x squared plus 4 are imaginary. Right? They're imaginary. They're plus or minus what, 2i? So, yeah, so this is irreducible. This word is a big deal. Irreducible, okay? Irreducible quadratic. That means that if I were to continue to factor, I would have to go into imaginaries. All right. There we go. Any questions on this so far? This is just the overview, and I'm going to do, all the rules and stuff. We're going to work some problems. All right, let's go to the next slide and let's work some examples. Okay, so the first one, here's our experience with P over Q. Find all real zeros. So really my first choice is factoring. I really wish that factored. If that factored, it would just be fantastic, right? Well, it doesn't factor. So that means that I've got to do I've got to resort to P over Q. So let's remind ourselves how that works, P over Q. So P is the factors of the constant. Okay, so the constant is 4. So P, so P is plus or minus, and it's always plus or minus. We need to figure out all the numbers that multiply to get 4. 1 times 4 and 2 times 2. Those are the factors of P. Q are the factors of the leading coefficient. The leading coefficient is the one with the biggest exponent, this one, 2. Well, the only way to get 2 is 1 times 2. Now, that's what P is and that's what Q. Where we're going is P over Q. So what I have to do is I have to take 1 and place it over everything in Q. So 1 over 1 is 1 over 2 is 1/2. And now I take the 2 and I place it over everything. So it's P over Q. So 2 over 1 is 2, and 2 over 2 is 1. I already have 1, so there's no reason for me to write it again. You don't have to duplicate the numbers. All right, so 4. 4 over 1 is 4, and 4 over 2 is 2. And I already have a 2, so I don't need to write that down. Okay, are we okay so far? Hopefully it's bringing back some memories. So really the good news is there are only 8 possible rational roots. Only 8. Either plus minus 1, plus minus 1/2, plus minus 2, or plus minus 4.
Does it always have to be in order of...
No, no, you can put them in any order. I usually do that, but no, it doesn't matter. It doesn't matter. You can write those numbers in any order. So here's where okay, so a little quick thing. I don't really ever do synthetic division with 1 and -1 because I can kind of do those in my head. And I'm not good with numbers in my head, so this is a plus for you guys if some of you aren't good with numbers in your head. The way to check 1 and -1 is if I put a 1 in for x, I need to get 0. And if I put a -1 in for x, I need to get 0. That means it's a root. So if I put 1 in here, I get 2, and that's what, 9. Yeah, that's not going to give me 0. 1 is not a root. So -1, I'm going to put a -1 in here. So that would give me, what, a -2 plus 7. That's what, 5 plus 4. Yeah, that's not going to give me 0. So 1 and -1 aren't going to work. There's no sense in me doing synthetic division with them. Now, you know, I'm not that lucky with these. Usually it takes me 3 or 4 tries to find a root. Some of you are probably extremely lucky and are going to get it on the first time, but not me. So I'm just going to say, I already did this, you know, several times, and I'm going to say the root was -2. And I'm going to show you how that works. Let's reminder of synthetic division. What I do is I put the root in the box, then I'm going to write these numbers down, the 2, the 7, the 4, the -4. Now here's a big deal here. With synthetic division, if I am missing a term in descending order, I have to put a 0 here. If I don't, I'm going to get an answer, but it's going to be wrong. Now with long division, that doesn't really matter that much, but with synthetic division, it is crucial. So I've got cubed, squared, first power, constant. I'm not missing anything, so I don't need to insert a 0, but I want you to be cautious for that. I don't want you to make that mistake. So what we do is we bring down the first number, the 2, and then I'm going to multiply, add, multiply, add. So multiply -2 times 4, -2 times 2 is -4. Add that, I get, what, 3. -2 times 3 is -6. Add down, I get -2. -2 times -2 is 4. Add down, I get 0. This is the remainder. This needs to be 0 for that to be a root. Okay. Now, I do need to talk about, because I had some students in the earlier class kind of forget. I just assumed that we would remember, but it was probably bad on me. If this was like let's say this was x to the 5th. X to the 5th. I would need to do this 3 times to get down to a quadratic. Right? My goal is to get down to a quadratic and then just translate it into a quadratic and do quadratic techniques, because we got tons of those. We've got factoring, we've got quadratic formula, we've got completing the square. I mean, we have tons of ways to solve quadratics. We don't want to do P over Q with a quadratic. So I would turn this into a quadratic, 2x squared plus 3x minus 2. But let's say that, you know, this was a to the 5th, and I had a much larger, and now I was down to a cubic, not to a quadratic. When I continue my synthetic division, I always continue with this new equation, whatever it is, wherever I found it. Do not go back to the original or you will never get down to a quadratic, ever. So you've got to continue your synthetic division with this equation. Okay, we could actually do that. We could keep going. I could say, and I have the 0. Let's do -2. It's actually another 0. Let's do -2 again. And instead, we're going to use the new equation, which is 2, 3, -2. Okay? So I multiply, -2 times 2 is -4. Add down, I get -1. -2 times -1 is 2. Add down, I get 0. See, -2 is a duplicate root. And I could just keep doing this if I wanted to, or I could stop and translate it. I'll just stop and translate it. This is 2x minus 1. I would set that equal to 0 because I'm looking for the roots, and I would get x is 1/2. I mean, that's what we would do. So my roots are x equals -2 with a multiplicity of 2 and 1/2. Those are my roots. Okay? Now, we could have stopped right here and factored that and gotten the exact same thing. This factored is, what, 2x minus 1, and it's x plus 2. Right? We would have had to do this, but I wanted to show you what happens if we have to continue. Well, you want to continue with this reduced equation. Don't ever go back to the original once you found a root. Because I got -2 as a root right here. That's a root. And I got -2 as a root right here. I got it twice. And you really want to check for that, because sometimes that happens, and we sometimes just kind of breeze by it and say, it's not going to happen again, and sometimes it does. So that's how I know. I was able to divide -2 out 2 different times with 2 different equations. Okay? How are we with P over Q? All right. Now let's go to Descartes' rule of signs. All right, so this is P of x. We want to determine sign changes of how many sign changes we have. So I'm going from a positive term to a negative term. That's one sign change. I'm going from a negative term to a negative term. There's no sign change there. Negative term to a negative term. There's no sign change there. So the number of positives is 1. And I can't subtract 2 from that. It gives me a negative number. So there's one positive real number, period. To determine, so that's what we asked. How many positive, how many negative, how many total? Okay, so that's positive. To determine negative, we first have to find P of -x. So what I'm going to have to do is put a -x everywhere there's an x and simplify. So I put -x cubed minus -x squared minus -x minus 3. So let's simplify. So -x cubed is -x cubed minus -x squared is a positive x squared, so x squared, minus a minus would be plus x, and then minus 3. Okay, so that's P of -x. Now we're going to do the same thing. Let's look for sign changes. Negative term to negative term, there's no sign change. Negative term to positive, oh, there we go, there's one sign change. I have a positive term to a negative term, oh, there's a second sign change. So this one has 2 sign changes. That means that the number of negative is going to be 2 or 0, because I have to take into account maybe they're imaginary, right? That's that whole -2 thing. So that's the number of negative ones, 2 or 0. Now total. Total has to be a combination of these two. I could have 1 positive and 2 negative, so I could have 3 real zeros. Or I could have 1 positive and 0 negative, or I could have 1. Those are my choices. And that's how we use Descartes' rule of signs. Okay? No, using it's just finding them. Now, you might, like a P over Q situation, you might want to do Descartes' rule of signs just to figure out for yourself, or what am I looking for? Am I looking for a positive number? Am I looking for a negative number? I mean, you might want to, just for yourself, but if I ask you to do it, that's all my purpose is find those totals. All right. So number 3, let's see, factor. Okay, so here we go. Here's our vocabulary words. Factor into linear and irreducible quadratic factors. Probably the most common mistake on quizzes and tests is not reading directions. If I ask you for linear and irreducible quadratic factors and you give me something that's not that, right? How can I give you credit if you give me something that's not that? That's what I'm asking for. So let's factor. This is in quadratic form. Okay, so the back sign is negative, so that means the signs have to be different. Let's see, I need something that multiplies to get an 8 and adds to get a 2. So what, 4 and 2? So 4 would be the positive one because I want this to be positive, 4 and 2. Okay, so let's stop and evaluate what we got going on. So we got two quadratic factors. Are either of them irreducible? Yes, this one is irreducible because if I keep going, I'm going to get imaginaries. Now this one is still good to go. We don't normally factor that, but this is factorable. And if we're not sure, we can just go up here and do a little scratch work. You know, x squared minus 2 equals 0. X squared is 2, so x is plus or minus root 2. So we can factor that. So let's do. So we have x squared plus 4 times x minus root 2, x plus root 2. Now I have satisfied the requirement for linear and irreducible quadratic factors. That's what it's telling me to do. So vocab, really important in this unit. Really important. Linear and irreducible means this. Now factor completely. Completely means all the way to linear factors. We're going to have imaginaries, everything else. All the way to linear factors is complete. So that means we need to deal with this, x squared plus 4. Again, if you don't know what that would be, let's do a little scratch work up here. X squared plus 4 is 0. X squared is negative 4. X is plus or minus the square root of negative 4, which we know we simplify to 2i, right? So we have x plus 2i, x minus 2i, x minus root 2, and x plus root 2. And that's when it says completely into linear factors with complex coefficients. Now I've got to do a side note here because there's a place students get a little confused, so stay with me for a minute. Let's say that I have a 0 of 2 and a 0 of negative 3. These are zeros. Now let's say I want those factors that correspond to those zeros. What do? Well, you probably do it without thinking, right? My factor here would be x minus 2. That would be the factor for 2. I'm going from a 0 to a factor. Important, again, vocabulary. If I ask you for zeros and you give me factors, that's a problem, right? So here, my factor would be x plus 3. I mean, we do this without thinking, but what is it that we're doing? We're doing x minus in front of it, right? X minus the 2, x minus the minus 3. The reason I'm saying that is because you're going to be faced with imaginary zeros that are a little more difficult than plus minus 2i. Let's say you have imaginary zeros of 1 plus or minus I. And we want to make factors out of those. If this is my 0, and I want the factor, I'm going to do the same thing I did up here, x minus. X minus 1 plus I, x minus 1 minus I. I am saying this because what I a lot of times get from students is students change these signs, these two signs. That's not the signs that change. It's these two that change, the conjugate signs. This is what changes. To get a factor, it's always x minus. Okay, so hopefully we're okay there. It stays like this. It stays just like that. Yeah. There's no parenthesis here. We're not going to keep going. It just stays just like that. Okay. All right. Our last example. Find a polynomial of degree 4 with leading coefficient of 1, quadratic coefficient of 12, linear coefficient of 8, no constant, and contains the point -1, 1. Whew. Okay. So it's a 4th degree with leading coefficient of 1. That means, y equals x to the 4th. Got that. It didn't say anything about a quadratic coefficient, a cubic coefficient. That does not mean that it's 0. That just means that we don't know what it is. Okay, so I've got to put it in there. I don't know what it is. I'm going to call it a, x cubed. I don't know what it is. Then we have a quadratic coefficient of 12, so plus 12x squared. A linear coefficient of 8, plus 8x. And there's no constant. And they give us a point, -1, 1. Why do you think they give us that point? To plug it in to find a, right? That's why they do that. Because we need to know what a is. So this is my x value, this is my y value. I'm going to substitute that in and solve for a. So y is 1. Let's see, we have -1 to the 4th plus a times -1 cubed. plus 12 times negative 1 squared plus 8 times negative 1. Okay, so let's clean that up. Negative 1 to the fourth is 1. Negative 1 cubed is negative 1, so minus a plus 12 minus 8. Okay, cleaning that up. So we solve for a, which we all are very good at doing that. So we get that a is 4. So now I can write my polynomial of degree 4. So y equals x to the fourth plus 4x cubed plus 12x squared plus 8x. This is one big category of problems that you'll be faced with when you're asked to find a polynomial given information. The other kind, which you probably had quite a few of last year, is you're given the roots and you're asked to find the polynomial. Remember that? So I just want to remind you, because there's a formula that goes with it that you can use if you want to. It's quite handy. If you want to use it, you don't have to. Let's say you're given the roots of, so this is just, another example that you'll be faced with. So let's say you have the roots of 2, negative 5, and 2i. Let's just say those are your roots. That's all they give you. We know that if you have the root of 2i, there's another one there, negative 2i. And just as a side note, if you had the root of square root of 2, you'd also have the root of negative square root of 2. They behave the same way. They always come in pairs. Think about your quadratic formula, right? Plus minus, square root. Okay. So we got this. So what would we do? There's some options. You can do the x minus and multiply everything out. You can do that. Or you can use this fun formula, x squared minus sum x plus product. Do you have to memorize the formula? No. You don't have to use it, but it just makes things faster, especially with imaginaries. What if I wanted to multiply these together? Well, that would be x minus 2i, x minus a minus 2i. It'd be kind of hard. I could do it. But why not do the formula? Why don't I add 2i minus 2i? I would get 0. So we're doing that, x squared minus 0x. What if I multiplied 2i times a negative 2i? I would get negative 4i squared, right? Multiply negative 4i squared. What's I squared? Negative 1. Negative 1 times negative 4 is a positive 4. So that would be my equation for this. It only works in pairs. This is squared. I could do it with these too. What if I add those together? I get negative 3. So x squared, it's minus some x, minus a minus, so plus 3x. And if I multiply them together, I get 10. And then I would just multiply these two together. Your answer is going to be all multiplied out. Okay? So that's just a reminder of another kind you will face. All right. How are we doing? That was a lot of review. That was a ton. There it goes again. Okay. We good?